equations are equations of a third parameter, like time, that is used to calculate the position of a moving object along a linear path. Here's an example. Let's say that from an initial position at 1,6, an object moves linearly with constant speed. It reaches 7:10 after 2 seconds and 13:14 after 4 seconds. Well, let's graph it and see what's going on. So we've got our initial position right here at 1,6. That's where it starts. So when time is 0, we're right there. Then this object that's moving 2 seconds later gets to 7:10. And then 2 seconds after that, it's at 13:14, which is right here. As you can see, those do appear to be lining up. So the object is moving at a constant speed in this direction. I've got a table of values down here, and besides the normal x and y that we usually track on in a linear equation, let's also look at what's happening with t as in time. So the initial point we say is t0 or t sub 0. That's when no time has passed. This is where we start. So this starts at 1,6 when time is 0. And then 2 seconds later, it's at 7:10. And then after 4 seconds total, we're at 13:14. Our job is to look for patterns in the progress of x and y as t is increasing, and see if we can come up with a way to predict where this moving object is going to be located, let's say at 100 seconds. So here's the data we have so far. Let's try a few little problems. Let's see if we can figure out where it would be after 6 seconds. Well, notice that so far what we have is the time changing every 2 seconds, right? 2 seconds later, 2 seconds later, and 6 seconds is just 2 seconds later. So whatever patterns exist so far are just going to continue at 6 seconds. Let's check the x's. The difference between these is 6, and the difference between these is 6. So we've got a steady increase of plus 6 every time for the x's when the time goes up by 2. So if we add 6, we get 19 would be the x-coordinate for the position of the moving object after 6 seconds. Let's check the y's. This is going up 4, and this is going up 4. So we've got a pattern of plus 4 in the y direction when seconds go up by 2. So if we add 4 more, we get 18. So the position of the moving object after 6 seconds is 1918. And it's handy that we can tell that by calculating, since our graph can only hold so many points. No matter how big your graph paper is, eventually you're going to run out of points. Okay, now we want to figure out where would this moving object be after 9 seconds. Okay, so this is a little more complicated because that's not an even number. But let's just keep increasing our chart and see what we can figure out. Okay, in 2 more seconds, we're at 8 seconds total. If I increase x by 6, I get 25. And if I increase the y by 4, I get 22. 9 is between 8 and 10, so I'm going to calculate 10 also. So after 2 more seconds, if I increase x by 6, I get 31. And if I increase y by 4, now I get 26. So 9 should be right in between here. So now what I could do is just average my x values and my y values right here. Halfway between 25 and 31 is just the average of 25 and 31, which is 28. So 28 is right in the middle there. And halfway between 22 and 26 is a little easier to figure out. That's just 24, right? So after 9 seconds, my moving object is at 28:24. Now that worked fine. Now let's say I wanted to know the position of the moving object after 100 seconds or an hour. I don't want to have to build this table of values forever. I want a different way. We want to generalize this formula. So what we do is we look at what happens when t increases by just 1. For every 1 second, what's happening to x and what's happening to y. So now let's look at the 8 and the 9. In between 8 and 9, what's the difference here? It's a difference of 3, right? So we're increasing by 3 in the x direction every time. And what's the difference here? Just 2. And that makes sense because those are half of these numbers because I'm looking at 1 second instead of 2. So every time t increases by 1, x is going to increase by 3. But where did it start? This row is very important for figuring out parametric equations. Here's what I'm about to figure out. If time is t instead of a number, what formula can I make with a t in it that'll give me the value of x that I want? Well, you always start with the initial position. X started at 1. And then I add the increase of x for every second, which is 3 times the number of seconds. So I get this little formula. Let's try it. Let's plug in t equals 4 and see if we really get the value that goes with 4. So if t was 4, I'd have 4 times 3, which is 12, plus 1, which is 13. And that is exactly correct. Okay, great. Let's do the same thing for y. So the initial position for y was 6, and then we add the increase for every second times t, 2t. All right, so there's our formula. And those are the parametric equations. And so for t seconds, for this last question, the position of the object is at 1 plus 3t, 6 plus 2t. And that's your introduction to parametric equations. I think that'll really help when you see problems like this in your homework.